Right, so for the oxygens, this is going to be a little bit more challenging, but it's not too bad. You'll notice that the amount of oxygens that we have is always dependent on both CO2 and H2O. That's why it gets a little bit more complicated because, CO2 is just based off of this. Like there were only one thing on each side that had oxygen in it, and this one we've got two on this side. So the pattern that we have going on here is that the number of oxygens that we have is always the number of waters that we have divided by 2, because oxygen, water only has one oxygen molecule in it, but oxygen is naturally a diatomic element. So it's going to be the number of waters that we have divided by 2, and then plus however many carbon dioxides we have, because there are 2 oxygens there in carbon dioxide, so we don't need to divide that one by 2. So that for oxygen, we'll have the number, that's the wrong color. Right. I'm going to have the number of H2O over 2, so the number of water molecules divided by 2, plus the number of CO2, carbon dioxide molecules. And you'll see that works out for all of them. We've got and this is, okay, so this is then how much goes in. So we'll have, I just put it in the wrong box. All right, and then so that's how much goes in, because oxygen is on this side of the reaction. And you'll see that this formula works out for all of the reactions, because you'll have 2 divided by 2 plus 1 is 2. 3 divided by 2 is 3 halves plus 2, that's 7 halves. 4 divided by 2 is 2 plus 3 is 5. So our formula works. And then for nitrogen, going in, we're just going to have the coefficient on the oxygen times 79 over 21. So it'll be number of oxygens times 79 over 21. All right, and then that same amount of nitrogen is going to come off. So you can write that down here as well, because none of it reacts. And then how much oxygen comes out? Well, most of the oxygen is going to get reacted, but 20% of the oxygen is going to stay. So we're going to call that, so we're going to have 0.2 times that number up here, which we're just going to call number of oxygens. And then actually we also need to account for the excess air up here, because the excess air goes in as well as comes out, so we need to multiply this whole thing by 1.2. I got a little quick there, that's not an exponent, it kind of looks like it, so I'm going to write it differently. I'll screw this over. All right. There. That gets a little weird there, but shouldn't make the boxes bigger. Sorry about that. But yeah, so we'll multiply it by 1.2 because 120% of the oxygen needed goes in, and then only 20% comes out. So that's how we're going to calculate the amount of each of these components that goes in and how much comes out.